All right. Good morning, ladies and gentlemen. So today we're going to be working on two AP first responses from the past, and the reason why we're doing this is to prepare for the AP test, and also to prepare for your test that we're going to have in not 1 but 2 days.
That's right.
And I really can't emphasize enough. When we are asking you to pause the video and work on these problems, you really got to pause the video and work on it. It doesn't matter if you mess up here. Who cares if you mess up here? So it's low risk, but you're not gonna really take it in and learn something if you don't give it a try first and then learn from your mistakes.
Yeah. You know, if you get it right, wonderful. And if you make a mistake, you're engaged so that when we go over how it should be done, then it'll make more sense. You'll learn.
Yeah, and so I challenge you guys today, you know, if you're not doing this every day, to really push yourself to put your thoughts on the page here, okay? So we're gonna start with this this physics question, this classic free response question from 1998. And so it says, so we've got this circuit here, and it says in the circuit that all the resistors, all these bulbs, have identical resistance. Assume that the battery maintains a constant potential difference between its terminal. Ooh, let's talk about this real quick. The internal resistance of the battery is assumed to be negligible. Look what I just did there. I used my finger to
Atta
follow
girl.
it. And that just means that it's just if it's 3 volts, it's 3 volts. You know?
See, batteries do two things. There's two things going on in a battery. There's a chemical reaction that provides what's called the electromotive force.
Whoop, whoop.
But there's also resistance to current flowing through a battery. So what they're saying is, just take a look at the electromotive force and ignore the resistance.
Yeah, so essentially everything we've been talking about, right? So, and the resistance of each light bulb remains constant. So the voltage from the battery, the electromotive force is constant, and then the resistance is gonna be the same for all of them, okay? So the first steps is to draw a diagram of the circuit in the box below using the following symbols. Real quick, check out, this is a reading exercise. You know, make sure you know where the letters go. It's not A, B, C, D right in a row. They kind of flip-flop things around. So
Yeah.
Label them accordingly. Here are your symbols. Draw your diagram in the box right here.
Okay, we've got it set up. So pause the video, give this a shot, and don't come back until you got something.
Yeah, pause the video. Pause it. And put this over here. We don't need that one anymore. Okay, so should we go ahead and show them?
And we're back.
And we're back.
Yeah, I'm going to come over there. So.
Okay. Oh yeah, that's a good idea. Okay, so you should have something that looks like this. So check this out. A is right here, C is the next one in line, B is right here all in series, and then D is over here. Okay.
Yeah, you can see these wires are on the outside. These wires on the outside of the two bulbs.
Yeah, and if you connected that to there, that's totally fine. I did that over here in my answer key.
Yeah.
And also, again, did you read? They're not using a light bulb symbol that we're used to. They're just using resistor. So you want to make sure you're doing what they ask you to do.
Okay. Now it doesn't have to look exactly like this, you know, as long as you've got this is in series with the battery, and then these two are in parallel. This one has 1, and this one has 2 in parallel.
You're good. Okay. So now, the next question here. Oh, actually, pause for a second. Notice how they don't give you any values here.
Right.
But they tell you that all the resistors are the same, and they tell you that the battery voltage is constant. So,
But they don't tell you what the battery voltage is.
They don't tell you what it is. So I'm gonna tell you right now. Make up a resistance and make it the easiest one you can. So I'm gonna suggest maybe make each resistor 1 ohm.
Cool.
Yeah. Okay. So as we come over here, it says list the bulbs in order of their brightness from brightest to least bright. Brightest to least bright.
Yep.
If any 2 or more bulbs have the same brightness, state which ones, and then justify your answer.
Okay, now first of all, think about what you're going to have to do in order to do this.
Okay.
What have we been doing in class?
So we have been starting with our you know our full circuit, and then we've been reducing it down to the equivalent resistance there.
Oh, that's right.
Right.
And
Okay, going.
where can you simplify? Take it step by step. And I think there's going to be 4 steps here, boys and girls.
Yeah, and so once you've done that, what do we normally do after that? We find
Well, you start from left to right, making it simpler until you have only one resistance, and you get the equivalent resistance.
okay.
And then you find the current for that one,
Uh-huh.
and then you work your way back to the start
Finding the voltage through different elements. Okay.
and current through different elements.
Voltage and current. Now, what is this question actually asking us for? It says it wants to know the brightness. What are we actually trying to find here?
Well, what variable is brightness?
Well, brightness has to do with power,
That's
right?
right.
And what are the two components of our power equation?
No, it's IV, intravenous.
Intravenous. So we need to know the current and the voltage in order to calculate the power for each of these bulbs
Yep.
to figure out the brightness.
Yep.
More power, more brightness. And you have to say that too.
Yeah.
You can't just, have your answers there. More power, more bright, and then rank those guys. Okay.
All right.
All right, so
So
you're gonna go ahead and pause the video, give that a try. Do not do it in this small space if you printed it out. Do it on a piece of paper, and then we'll come back and talk about it.
all right, and we're back.
Okay, we're back. So
Take your cheat sheet.
all right, so let's go ahead and draw what this looks like. And with this, I'm gonna move you over. All right, so we've got our battery here, and we've got the first one, second one, third one. That's pretty big.
Oh, look at that. I like the way you did that.
Oh, I always do that. I forget that one right there. Okay. And we said that we're gonna just go ahead and give them 1 ohm, right, of resistance.
Yeah.
Just make your life easy. If you want to choose 1.5, 2, go for it.
3.14.
Do whatever you want. They're just all have to be the same. And I am gonna make the battery. Oh, I forgot to mention this to them. I'm just gonna say 3 volts. 2 batteries, 3 volts.
It doesn't matter. Anything you choose is going to work.
Yeah, only one. I only say 1 battery here, but whatever.
All right, what
Okay.
can we reduce? What can we get rid of first? What can we simplify?
So I'm gonna actually simplify these two first.
I like that.
Okay, so let's go ahead and make it look like this. So battery. Okay, 1, 2. See, I always do that. Okay, like that. And if I'm going to, so these two are in series, right?
Series is you just add them up. 1 plus
Just
1
add
is?
up 2. Okay, this is still 1 ohm, yeah?
Yep.
Okay. I'm gonna go ahead and try to do what Mr. Boykin does with his handy dandy marker trick here. 3 volts, okay? But wait, there's more, right? Are we done yet?
No, we're not. What can we simplify next, boys and girls?
Let's go ahead and chop this guy down. I'm gonna go over here. Okay, so battery. And I'm just gonna combine
That parallel.
these two. And I'm gonna go ahead and use my calculator for that. So, it's
So
just
that
gonna
parallel is the, and go ahead and show the work. Don't just
Oh,
take,
okay.
do your
That's
calculator.
a good idea. Let me write my other stuff in first here. So I've got 1 ohm here,
We don't know what that is yet.
3 volts here. Okay, so we're gonna do 1 over 1 ohm plus 1 over 2 ohms.
That's 1 over 1. That's 1 plus 1/2
That's
is
gonna be 3.
3/2. But that's not the answer.
Okay, and check this out. When Miss Moore first did this through, I was like, I got really hung up on this. I'm like, 1.5. How do I know that's not right? It's not. Oh, I guess 1.5. It's not less than both of the resistors.
Yeah, that's the inverse. So you
Yeah.
gotta flip it.
Okay, which equals 0.7 ohms. Okay, and we're gonna use 0.7 just because it's easier for Miss Moore to think about. Okay. All right, so here we are. Are we done yet?
Well, nope, because you need a single resistance, and we got 2.
Okay, so here we go, right here. Okay, and now Miss Moore is happy. We're in the beginning, 3 volts here. And now we just add these up, so 1.7 ohms.
Okay, now once we get it down to 1 equivalent resistance, what's that thing we do?
The next step that we have is finding the current through the current that the battery sees, right? Because the battery's
Right.
dim. The battery only sees this resistance. What's the current? How many joules per second is that? Are those electrons going to be pushed through
Coulombs
there?
per second.
Sorry, coulombs per second. Okay.
Well,
okay.
V equals IR, so I V over R.
Okay, what's our voltage here? Divided by our resistance is 1.7 ohms. And you know what? Let me get my cheat sheet.
Oh, you've already got it
I'm just
done.
gonna cheat sheet it here. Okay, I get 1.8 here.
1.8 amperes.
Right, because you guys should have this done already, right?
Yeah.
Okay, so that means that this is 1.8 right here. It also means that this is
1.8. It also means that. And it also means that.
okay.
Boom!
Boom. Okay. All right. So now I'm gonna go ahead and work backwards. And what I want to do is I want to find too many markers. I want to find the voltage drop across each of these elements. Okay.
Yeah.
So I want to figure out what the voltage is here, and I want to figure out what the voltage is right here.
V is IR.
Okay.
So that voltage is going to be the current times the resistance.
Okay, well, our current, this is in series. The current's going to be the same throughout,
That's
right?
right. Uh-huh.
So 1.8 amps times the, oh wait, V equals, that's the same.
V equals IR.
IR, there we go. And our resistance here is 1 ohm. That's easy.
That's going to be 1.8.
So this
Okay,
is-
now boys and girls, the loop rule says that the ups equal the downs. So we got 3 volts and we got 1.8. What's that going to be?
1.2. Now, if you insist on doing that multiplication, 1.8 times 0.7 will give you 1.2.
Boom, 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 boom.
All
Okay.
right, now
So-
we come over here. So that means that this is also
1.8 volts.
Okay. Now, what do we know about the voltage when we have something in parallel?
When it's in parallel, the potential difference is the same. The voltage is the same.
So this 1.2 volts is going to go to both of these. Both of them is going to be 1.2 volts.
Yeah.
Okay. Okay. So as I come over here, let's talk about the voltage here.
Yeah.
Okay, so this is going to be 1.8 volts. All right. And this is still just 1.2 volts, right? Okay.
Yeah, but now what we've got is,
Something in series.
yep, so,
And we know that the ups equal the downs, right?
uh-huh.
So if the total, I don't know if that makes sense, but if the total here is 1.2, they have to both add up to 1.2. And they're both the same resistance, so that means their voltage has to be the same, right?
The voltage is the same, so it's going to be split evenly.
So that's 0.6 volts, right?
Yep.
0.6 volts, like that.
Okay, now we need to find out how much current goes through that top 1 ohm resistor and how much current goes through.
Well, okay, I'm gonna stop for a second. Why do we need to figure out the current? What are we doing here?
Yep,
We
we
need the
want to know
power.
how bright the bulbs are, and that's the power.
Okay, so right now, and you know what? Let me pause for a second. Let me ABCD these real quick, so that way we can. So this is A. Oh, looks like I labeled them wrong here. Nice job, Miss Moore.
Here, let's see. The
A.
one after that is C.
B.
That's C, and that's D.
Look at that. I labeled it ABCD.
Yeah.
That's right. These things happen. Okay.
All right. So now, for the one on the left, we can get the power output of that. That's
Yeah.
IV.
Yeah. So
The current is
So of
1.8.
A, so the current is 1.8 right here. Amperes times the voltage, which is also 1.8. Okay, when I multiply those two together, I get 3.6.
So that's 3.6 watts,
What?
and that's A.
Yeah, that's for A. Okay, so let's talk about, we need to get now the power for B, power for C, and the power for D. Okay, so Mr. Boykin, that's why you're saying we need the current, right?
Yeah.
Okay, so let's go back to the current. So, let's just start with this one right here. How can
Well,
we
you know
find-
what? If we've got the resistance and we've got the voltage, we could put Ohm's law.
Oh, we could. You're right.
We could solve, let's see, P equals IV. We don't have the current.
Let's walk through that with them. So P equals IV, and we don't have the current, right? So what is the equation
Ohm's
for
law,
current?
I is V over R.
So we could put this right here, V over R like that.
Yep.
So that's really P equals V squared over R, right?
Yeah.
Okay.
Well,
so
that makes it much different, much easier.
That does. You know what I was gonna do is I was gonna find the current through here and just by doing 1.2 divided by 1,
Yeah.
right? And then here I was gonna do
Well, 1.2 divided by 1 is 1.2. So
right?
go ahead and put that in up here.
yeah. Okay, so we'll just say right here,
Yeah.
1.2. Okay, and then if you think about this this is gonna be really easy. 0.6 volts divided by 1. These are both gonna be
Now hold on a
0.6.
second. We got 1.8 amps coming in. 1.2 goes up there. How much is left to go through these two? Right? Because what happens to the current when it gets right here? It
0.6.
splits. We get 1.2 going here. So how much is left?
So this has got to be 0.6 amps.
0.6
right
amperes.
here, right? And they both receive 0.6 amps.
Yep.
Right? Okay, but let's go ahead and do what Mr. Boykin was talking about too. So if you're wondering what we just did right there, if you kind of like lost us there, we were just using this equation right here, volts over a resistance, and we put one
V squared.
no,
No, you're right. No,
1.2,
you're right.
Just so they can see it over 1 ohm.
Yeah.
Okay, and we said that that's 1.2 right there. And then what Mr. Boykin is saying is that we have 1.8 amps going this way and this way. How much is going each way? Well, if we've got 1.2 going this way, that means that this way we have to have
What's left?
0.6.
Yeah.
And because they're in series, they're both going to see the same.
Now let's just do that V squared over
Yeah,
R
I
on
think
that
so.
one.
Which one you want to do, the D?
Yeah.
Okay. So for D, so if we use V squared over R over here,
The V is 1.2 volts squared over 1. 1.2 times 1.2, I can't do that in my head. That's going to be 1.44, isn't it?
1.44.
Boom, 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 boom!
Okay, and I got 1.4 when I did my work.
Yeah, 1.4
earlier.
will work.
We'll call it 1.4. Okay, now check this out. So if you wanted to just stick with your I times V, if you did right here, if you did 1.2 times the voltage times 3, you would also get that. Okay. No, sorry.
Not times 3.
Not times 3, times 1.2 times 1.2, right?
Yep.
The current times the
Which
voltage.
is the same thing.
Yeah.
Now here's the thing. Before we do any calculations on C and B here, they're both the same resistance. They both have the same current. They both have the same voltage. They're going to be the same brightness. They'll be the same power.
Yep. They've got the same. Both of these two things are the same.
So that's going to be the current times the voltage. It's 0.6 amps times 0.6 volts. 6 times 6 is 36. That's going to be 0.036? No, that's not going to be 3 points.
You're right. No, it's not.
Calculator.
Oh, yeah. Ms. Moore can't.
I can't either.
0.6 times 0.6, 0.36. Oh,
0.36.
I put
Just
this in my
yeah.
calculator wrong last time. Okay, 0.36.
And the other one's going to be 0.36 as well.
Yeah.
So now, the most important question when you got through doing all this, what was the question we're answering?
So the question is, which one will be the
You always want to go back to the
Yeah, it
the
says list the
question.
light bulbs in order of their brightness from brightest to least. Okay,
Okay,
so
which one's going to be brightest?
so more power equals more bright, right?
Yes.
And that's important. Okay, so now which one has the most power? This
A.
is going to be our brightest. Now, how should we write it? Do we say number 1?
I do. Yeah, I say A is brightest.
You know, number 1.
B is number 2. Or not B, I'm sorry. D is number 2. And then a tie for number 3 will be the other two.
Okay. And do we need to go into like a little bit more detail, or it just says justify your answer? Is the math enough to justify, or do we need
Yeah,
to?
the math is enough to justify it.
Yeah.
Now here, notice that the one bulb is 3.6 watts. That's a lot brighter than the other two, right?
Wait, where are you looking at? Sorry, Brian?
I'm looking at our
Oh, right
answers
here- oh,
down
right here,
here.
this
So
one.
that's 3.6, and the others are pretty weak. We have this set up over here.
We do. Okay, so let's
Turn the
check
lights
it.
off over there, will you?
Oh, that's a good idea. Dang, when I was doing my work, I think I must have done this one in my head. I did 0.6 times 0.6 and I said 1.2. I added them. Okay, so so this is
the setup.
A, C, B, D.
Okay, this one lights up. That's the 3.6 watts. This one, nope.
1.4 watts.
This one,
Is there barely anything you see it in there?
barely.
I've noticed that it's hard to see things light on the camera when I upload stuff.
Yeah.
But ultimately, even though you can't see it, there's a little bit of lightness there. But and these ones are, I mean, it's hard to see.
Yep.
Right.
So
Okay.
all the current's going through this. The current splits here, so neither one of these gets the same amount of current as this one does. So this one's brighter. These two are much dimmer, and we've calculated how actually the power output that we've got.
Yeah. Okay. So we got those done.
Turn the lights
Let's
back
go
on.
ahead and take a look at the next part of this question. So the next part says C. So bulb D is then removed from its socket. Describe the change in brightness, if any, of bulb A when bulb D is removed from its socket. Justify your answer.
Okay, so
Let's look at our diagram first, quick. Up here.
I like that.
So we want to know
I
if
like
we
that.
unscrew this, okay, how is that going to affect this? And what? So we'll talk a little bit before we let you go here to work on it. What kind of circuit is this without the D involved?
Okay, all right, cut them loose.
Okay, put a pause on it.
Give
Go
it a
ahead and work on
shot
this
before you
one.
come back.
And should we cheat sheet first? Should we?
Not yet. Okay, no, they've paused.
Yeah.
And now they're back, and we're going to show them.
Okay. All right. So we are going to. Should I unscrew the bulb first, or should I plug it in? First?
Plug it in first.
Oh yes, that way they can see it. Okay, so.
We want to know what happens to this. Go ahead. When you unscrew.
Oh, we don't have these. These.
Ooh, it got dimmer.
Oh.
Oh. Okay.
It's like Christmas lights.
So this one got dimmer.
So I unscrew, dimmer.
Yep.
Okay.
Is that what you had, boys and girls?
So the real question is, why is this happening? Because you have to justify your answer. So if you got that, that's worth 1 point on the test. So if you said, Miss Moore, this light will get dimmer, the next question is why? Well, so when we take this resistor out of the circuit, this becomes a series circuit.
And you know what it does become a series circuit, but first of all, what is this parallel part doing? Let's go over to the third one here.
1, 2, 3, right here.
And notice that parallel part has much less resistance than the one bulb by itself. So there's less resistance there. And this is just like in the that's weird thing. Okay, so it's not gonna light up. So there's less resistance when you've got that parallel.
When you have a circuit in parallel, it decreases the resistance, right?
Uh-huh.
Now that's a good thing, because if you decrease the resistance, the current is going to increase.
So there's more current through this guy, so that's why it was brighter.
So it's happy. Now when we take this resistor out of the equation, now we just have a series circuit. And in a series circuit, well, when you have your resistors here, well, we're basically going to decrease the resistance from what it previously was.
Yeah.
So by decreasing the we're increasing the resistance.
Yep.
By increasing the resistance, we are now decreasing the current and not as bright.
That's right. Before, the total circuit was 1.7 ohms resistance. Now, when you take that D
good.
out, now we've got 1 plus 1 plus 1. We've got
That's a
3
great way to look at it.
ohms resistance.
Yeah, and we know that if we have less current, we're gonna have less power.
That's right.
Right? I forgot we talked about that.
Okay, so now what's the next thing they need
yeah.
to do?
Okay, so now describe the change in the brightness, if any, of bulb B when bulb D is removed from the socket. Justify your answer.
So what? Go ahead.
Oh yeah, we can. Did you hide it on the last video?
No, don't go back. Don't go back.
Okay, so what happens to B when we take D out of the equation.
So give this a shot. See if you can figure it out for your own. Pause the video, and then we'll come back and show you.
Okay. Will you hit the lights? It's working. Hit the lights.
Although this compensates for the exposure.
Yeah. Okay. Oh, does it? Oh,
Yeah.
dang it.
But that's okay.
I know. I noticed that when I showed the kids the with the zaps, you can't even
Yeah.
see them on there. Okay, so we want to know what happens to this one. This is B over
Yep.
here. Okay,
It lights up.
it lights up.
And now notice all of these are about the same brightness.
Mm-hmm.
And that's because they're the same resistance. They've got the same current traveling through them. All right, before there was the current split through these guys, and then when you take that out, now the current doesn't split, it all goes through these other two.
Okay, so so why is this? And so when we talk, sorry.
I'm doing it.
So when we talk about our answer for this one, we want to talk about having access to the battery here. So when I get rid of this guy right here, that means that each of these bulbs is going to receive equal access to the battery. The current through them is going to be the same. And so we have, our power is going to be the same.
Yeah.
The power output is going to be the same.
And what happens is, well, let's see, if you've got 3 1-ohm resistors in series, the total resistance is 3. If you've got 3 volts, what's the current?
It's going to be 1 ampere.
So you got 1, instead it goes from 1.8 through the 1 bulb to 1 ampere. But before, how much current we had? Only 0.6 of an amp going through these two.
Oh, that's so mathematically looking at it, that's a great point, right? If we're ignoring this right here, we will have only 1 amp. How'd you get that 1 amp again, Mr. Boykin? And we looked at the voltage over the resistance. The voltage is 3 volts.
If it's just a series circuit, you've got a total of 3 ohms.
3 ohms and 3 volts.
And if you want to know that's 3 volts divided by 3 ohms, that gives you 1 ampere. Now, an important thing, notice how having all of this written out with all the stuff on it allows you to understand and make sense out of things as you go to explaining. A diagram is a wonderful thing.
Okay, so that is the last question there. I think we justified pretty well there. So that was the first question.
Yeah.
And how much time are we got on there? Are we going?
That's 27 minutes.
Okay. So
That's half a period.
So so the next thing that we're going to be having you guys do for quote homework, if you don't finish this on class.
Well, it's classwork.
Yeah, classwork. Is this AP question here. So it says some students want to know what gets used up in an incandescent light bulb when it is in series with a resistor.
Okay, now first let's stop right there. What is an incandescent light bulb? These little bulbs that we're using are incandescent light bulbs. They have a filament that heats up. That's not like an LED.
Yeah,
An LED doesn't work that way. A compact fluorescent tube, these kinds of fluorescent lights don't work that way. An incandescent bulb has a current going through it and gets hot.
So that's what it looks like there. And you're going to want to draw that. Let's see. Some students want to know what gets used up in an incandescent light bulb when it is in series with a resistor. Current energy, or both. Okay, what's getting used up? Is it current being used up, energy, or both? They come up with the following 2 questions. Here are their questions. Number 1. In 1 second, do fewer electrons leave the bulb than enter the bulb?
Oh.
And number 2, does the electric potential energy of electrons change while inside the bulb? Okay. So the students have an adjusted, this is what the kids have access to. The students have an adjustable power source, insulated wire, light bulbs, resistors, switches, voltmeters, ammeters, and other standard lab equipment. Assume that the power supply and voltmeter are marked in 10th volt increments, and the ammeters are marked in 100 hundredths of ampere increments. Okay, so no adjustable power source. Okay, so describe an experimental procedure that could be used to answer questions 1 and 2 above. So as a teacher, as I'm standing in the classroom, student A says, Miss Moore, in 1 second, do fewer electrons leave the bulb than enter the bulb? How would I explain that to them using how could we create an experiment to help answer that question?
I know.
And same thing for my second question. So describe an experimental procedure that could be used to answer questions 1 and 2 above. In your description, state the measurements you would make and how you would use the equipment to make them.
Okay, so now understand that's all we're doing. How you going? What are you going to use? How are you going to hook it up? And then what measurements are you going to make? You don't tell them what measurements. Don't do anything more than they're asking you.
It also asks you to include a neat label diagram of your setup. So it's kind of like when Miss Moore would if Miss Moore handed you a lab procedure and it just had the procedure for what to do.
Yeah,
Just the steps.
and I think we've done something. We've done several
Oh, that's
labs.
weird.
So if you think back of what we've done, it'll tell you what to do. Now here's the thing. What is this? This is the 2015 AP Physics free response question. What are they trying to do? They're trying to figure out how much you know, what you can do. So that's what we're trying to do right now.
So let's look at the next question here. So once you write your description, your procedure here,
Yeah.
this question right here is it says explain how the data from the experiment you described can be used to answer question 1. So here's where you'll do the describing for how to answer, how what you're doing answers the first one.
And question 1 is about in 1 second, do fewer electrons leave the bulb than enter the bulb?
Okay. And then for number 2, that's when you answer the student's question for number 2.
Yeah.
Does the electric potential energy of electrons change while inside the bulb? Now, when you hear these questions, you should say no and no, right? So, do fewer electrons leave the bulb than enter the bulb? As we go here to here, the answer is no, but we have to show them, we have to show them that we know that.
Yeah,
right?
that's the way science works.
Yeah.
Because I said so,
It doesn't. No. Cut it. Okay, so, and then do we want to give them like a little hint about like what to focus on?
Well, I would say let them go. And
Okay.
how much do you want them to do? Do you want them to do all 3 of these on the front now?
Let's see. Okay. And then let's see. Is there a back page here? There is. Okay. So a light bulb is non-ohmic if its resistance changes as a function of current. Your setup from part A is to be used or modified to determine whether the light bulb is non-ohmic. So whatever you come up with up here, you're going to be using over here.
Yeah.
What does non-ohmic mean again?
It means that even though that something heats up, its resistance doesn't change. Now with these light bulbs, they heat up, the resistance changes, but
We'll
the
pretend like they
ohmic
don't.
is an ideal resistor that maintains its value.
Okay. And what's the one thing that could change a non-ohmic resistor? What could we change to measure this? What does it say here?
A light bulb, its resistance changes as a function of current. Well, change the current, see if the resistance changes.
Okay. So how, if at all, does the setup need to be modified? In other words, how do you change the current? And then what additional data, if any, would be collected? And then lastly, this is a really great question, something you should always be thinking about as we do our labs. How would you analyze the data to determine whether the bulb is non-ohmic? Include a discussion of how the uncertainties in the voltmeter and ammeter would affect your argument for concluding whether the resistor is non-ohmic. Okay?
So you
That's
want
a
to cut
lot.
them loose here?
Yep. Go ahead and finish up that if you response question, and we're gonna have the test soon, so make sure you're working hard here.